Welcome everyone, lecture number 22. Today in this lecture we will discuss application of Laplace transform in solving ordinary differential equation with constant coefficient. So let us consider the nth order differential equation with constant coefficient. D n y over dt n plus a1 dn minus 1y over dtn minus 1 plus a2 dn minus 2y over dtn minus 2, and here I have a and y is equal to some function of t here. Okay, where a1, a2, an, all these are constant, and here we are given some initial condition that y0 is suppose k0, y dash 0 is k1, y double dash means double derivative at 0 is k2. These are some initial conditions that are given to us, and this is n minus 1th initial condition, where k0, k1, k2, kn minus 1, these are all constants. So we are given the ordinary differential equation of nth order with some initial conditions. So we have to solve this using Laplace transform. So the method of solving such type of equation is that first we have to take the Laplace transform of this equation both sides. Let this equation be equation number 1. So the procedure to find the solution is, first of all, take Laplace transform of equation 1 both side. हम दोनों साइड इस इक्वेशन का लाप्लास ट्रांसफॉर्म लेंगे. Then by linearity property, that Laplace transform will go inside the bracket and it will work on each term. Okay. So after that, when you apply Laplace transform and use the formula of derivatives to find the Laplace transform of that differential equation, then that differential equation, after applying the initial condition, will convert it into algebraic equation. So equation 1 will convert into an algebraic equation. Okay. Then when the equation converted into algebraic equation, we find the solution of that algebraic equation by taking the inverse Laplace transform. So now by taking inverse Laplace transform, required solution is obtained. So let us do one problem on this ordinary differential equation. So let me take one example. Example is solve d square minus d minus 6y is equal to 2. T is greater than 0 and initial condition is y is equal to 1. And dy is equal to 0 when t is equal to 0. Means you are given that y at 0 is 1 and d y dash at 0 is also sorry, y0 is 1 and y dash 0 is 0. Okay, so let us solve this. We are given this equation. So this equation can be written as d2y over dt square minus dy over dt minus 6y is equal to 2. Okay, or you can also write this as y double dash t minus y dash t minus 6y is equal to 2. So we'll take Laplace transform of this equation both sides. Okay, so let me first write it for the whole equation. L of y dash t minus 6 L of y is equal to L of 2. Okay, so L of y dash is, if you remember, is p square Laplace of yt. You have to remember all the formulas. Minus py at 0 minus y dash at 0. This is only for this expression. Minus L of y dash. Let me put it inside the bracket. Minus L of y dash is PL of yt minus y at 0 minus 6 Laplace of y t. I should write t here. And this is 2 upon p because Laplace of 1 is 1 upon p. So you can apply this condition. This condition is y0 is 1 and y dash at 0 is 0. So we'll put here 1 and here 0. We'll put here 1. Okay. So applying the initial conditions, applying initial condition, we get, I'm writing on the next page, p square Laplace of yt minus p. Here you will get minus p and here it is 0. So I'm just closing it here. Minus pl of yt minus 1 minus 6 L of yt is equal to 2 upon p. That's done. This have to be done very carefully because mistake at this stage will make the whole solution wrong. Okay, so we have to take care at this point. Now what we'll do here is we'll take L of yt common. So L of yt is common, then we have p square from this bracket, and from this bracket we have minus p, and from this we have minus 6, and what is left is minus p and here plus 1 only is equal to 2 upon p. Now we find the value of Laplace of yt, which is equal to 2 upon p plus p minus 1 whole divided by p square minus p minus 6. So when you solve it, you have p square minus p plus 2 and p into p square minus p minus 6. You can you can factorize it. So when you do the factors, you will have p square minus p plus 2 over p into p plus 2 into p minus 3. This is the value of L of yt. Now at this stage, we'll take the Laplace inverse. Taking inverse Laplace transform, mark this as equation number 2. Of equation number 2. So when you take Laplace inverse of L of yt is simply yt. Okay. So we have L inverse of L of yt means we have only yt here. And here we have L inverse of p square minus p plus 2 over p into p plus 2 into p minus 3. Now you know very well how to solve it. We have to do the partial fractions of this expression. So after doing partial fractions, you will have L inverse of, I am writing it here directly, I am not showing you the partial fractions. You can do it very well. 4 upon 5 into p plus 2 plus 8 divided by 15 into p minus 3. These are the partial fractions of this function. Now take the Laplace inverse of each term. So Laplace inverse of this term is minus 1 upon 3 only, and its Laplace inverse is 4 upon 5 e raised to the power minus 2t, and its Laplace inverse is 8 upon 15 e raised to the power 3t. That's all. This is the required answer of the given ordinary differential equation. Okay. Let us do one more problem. You can do it with me by yourself. So simultaneously you can also try the solution of this equation. Y double dash t minus 3y dash t plus 2yt is equal to 4 e raised to the power 2t. And the initial condition is y0 is minus 3 and y dash 0 is 5. In some questions, these initial conditions are not given. If these are not given, we suppose any constant at the place of these initial conditions. You can take any constant, like you can take the value of y0 as a or x1 or something else, a, b, c, any constant. The answer will come in terms of those constants. Okay. Solution. So we'll take the Laplace transform again of this equation, taking Laplace transform of the given equation. We get you will get p square into Laplace of yt minus py at 0 minus y dash at 0. Okay, this is for the first term. Then for the second term, it is minus 3 p Laplace of yt minus y at 0 again, and for third term it is 2 Laplace of yt, and here we have Laplace transform of e raised to the power 2t. Okay, this implies y at 0 is given to us as minus 3 and y dash at 0 is 5. So applying the initial conditions, applying initial conditions, we have p square Laplace of yt minus 3p, sorry, it is minus 3, so it is plus 3p minus 5. Okay, minus 3 p into L of yt minus y at 0 is minus 3, so it will be plus 3 plus 2 Laplace of yt is equal to 4 upon p minus 2. Again we take L of yt common as usual. We have L of yt common. So we have p square from this bracket minus 3p from this bracket and plus 2 from this bracket, and here we have plus 3p and here we have minus 9 and minus 15 minus 5, so plus 3p minus 14 is equal to 4 upon p minus 2. Okay, so value of L of yt is 4 upon p minus 2 minus 3p plus 14 over p square minus 3p plus 2. So what we'll do here is, instead of mixing this with these terms, let us separate them at this stage. Uh, you can take this with this, and you can separate these two. So we will have Laplace of yt as 4 upon p minus 2 into this. Okay, p minus 2 into p square minus 3p plus 2, and it is minus 3p upon this, p square minus 3p plus 2, and just 14 upon this, 14 upon p square minus 3p plus 2. Okay, and now we do the factors of this. So we have p minus 1 into p minus 2. So it will be, when you multiply p minus 2 with this, you will have p minus 2 whole square into p minus 1. And it is 3p over p minus 1 into p minus 2, p minus 1 into p minus 2. Now we'll take the Laplace inverse of each term. Now taking inverse Laplace transform both sides. We have yt is equal to L inverse of 4 upon p minus 2 whole square into p minus 1 minus 3 L inverse of p upon p minus 1 into p minus 2 plus 14 into L inverse of 1 upon p minus 1 into p minus 2. So you have to do the partial fractions of each term. So the partial fractions are L inverse of 4 upon p minus 1 plus 12 minus 4p over p minus 2 whole square. These are the partial fractions of this expression. And here we have minus 1 upon p minus 1 plus 2 upon p minus 2. I'm not showing the method of partial fraction here because that makes the solution very lengthy. You can try it by yourself. L inverse of minus 1 upon p minus 1 plus 1 upon p minus 2. So yt is L inverse 4 into L inverse of 1 upon P minus 1 minus this 12 will combine with this and 4P will combine with this. We can separate these two. So we have L inverse of 12 upon P minus 2 whole square because we have 12, so we have positive sign here, and with 4 we have negative sign. P upon P minus 2 whole square. That's done with this. Okay, and for the next one, this 3 into Laplace inverse of 1 upon P minus 1, and it is minus 6 into Laplace inverse of 1 upon P minus 2, minus 14 into Laplace inverse of 1 upon P minus 1, plus 14 into Laplace inverse of 1 upon P minus 2. Now it is very easy. So it is 4a exponential t plus 12 exponential 2t by method, first shifting property, and then Laplace inverse of 1 upon P square, and here the same thing is here, 2t into Laplace inverse of, it is P minus 2 and it is only P, so we cannot apply the first shifting property here. So what we do here is we write it as it is. अभी इसको ऐसे ही लिखा रहने दीजिए, and ये exponential 2t will not come here. Okay, and here we have 3 e raised power t minus 6 e raised power 2t minus 14 e raised power t plus 14 e raised power 2t. Okay, now it is 4 e raised power t, this and this, so it is 7 and minus 14, so minus 7 e raised power t, that is left, minus 7 e raised power t. Okay, and this is minus 6 and this is plus 14, so this is 8 e raised power 2t, that will also cancel, and it is 12 e raised power 2t, and the Laplace inverse of 1 upon p square is t, minus 4 into Laplace inverse of, here will make p minus 2 and plus 2. Okay, so one of this p minus 2 will combine with this and 2 with this. Okay, we separate them, so we write plus 8 e raised power 2t plus 12 t raised power 2t minus 4 Laplace inverse of p minus 2 upon p minus 2 whole square, so that is p minus 2. Okay, minus 8 into Laplace inverse of p minus 2 whole square. Now yt is minus 7 e raised power t plus 8 e raised power 2t plus 12t e raised power 2t, and here minus 4 e raised power 2t, and this is 8 minus 8 into e raised power 2t, and then Laplace inverse of 1 upon p square, which is t. Okay, so it is 8 e raised power 2t into t. So again we can combine these two, and this can combine with this. So this is minus 7 e raised power t plus 4 e raised to the power 2t plus 4 e raised power 2t into t. This is the answer. Okay, you can try this question for your practice. Solve y triple dash t minus 2y double dash t plus 5y dash t is equal to 0, and the conditions are y0 is 0, y dash 0 is 1, and y at pi by 8 is 1. This condition is used at the last when you get the value of yt, because you will have y double dash t also there when you apply Laplace transform, but the initial condition is not given for that y double dash 0, so you assume some constant value for that. So at last when you solve this equation, you will have that constant somewhere. So to find the value of that constant, you'll use this condition. Okay, this is the hint for this question. You try it yourself. Okay, thank you so much for watching the video. I hope you understand the lecture. Okay.